Okay, this is section 4.8, begins on page 212. And we have to learn a few things, but most of it you already know. I'm going to reiterate it. I want you to look with me at the core concept on page 212. And let's see if we can just read it. If not, I'll demonstrate it for you on the board. Are you looking at it? Core concept. Page 212. This is stuff you already know. But I wanted to reiterate the vocabulary that's necessary for you to talk about it properly or to read it properly. If you've got a polynomial, I think you can all recognize a polynomial now, right? If you put a number in the box for synthetic division and get a 0 for a remainder, then we say two things. One of two things. That k, the thing we put in the box, that's what I'm going to call it, is k, whatever number that is. If you get a 0 for a remainder, then k is a 0 or a solution of that polynomial. Yeah? If you turn it into a factor, that is, wrap parentheses around it, stick an x in there, it's going to be x minus k. That's a factor that comes from that 0. We've done a lot of that already. They give you the zeros, the first thing you do is write the factors they came from, and you write x minus whatever those zeros were. You recall? Okay, so if k is a 0, then x minus k is a factor. We call it a factor. Get used to the vocabulary. K is also a solution or a root. You've heard me refer to it that way also. So solutions, zeros, roots, they are all synonyms. However, an x-intercept is a real root or a real 0. You can expect, if it's an n-degree polynomial, you can expect n solutions. But that doesn't mean you can always expect n real solutions, right? Okay, so look at example 1. What it says to do is it says graph the function. That's all you get, graph the function. What are you going to do? Where? On your calculator, right. But make sure that when you duplicate it, because remember you guys have to take paper pencil tests in here, right? So you will have to duplicate graphs. When it says graph the function, it doesn't say graph the function in your calculator and you're done. It says graph the function, which means you're going to have to produce it on a grid like this by hand. And so there's certain values that you need to be able to find with your calculator, and you already know how to find them all. If you can find the zeros and the maximums and the minimums, we call those turning points, the actual place where they are, and get them graphed as closely as possible on here, that should give you a really great indicator on how the thing's going to shape up. So really quickly, I'm not going to spend a lot of time on this because you already have all these skills. We're just going to practice what they want us to do here. So we put in the calculator exactly as it's written in example 1. We have 1/6, so I am going to put that in parentheses. Divided by 6, that's the first one leading off. Parenthesis, again, x plus 3. Do not hit graph when you're done typing it in, unless you already have. Get back to this y equals screen. X minus 2, and we're going to square that. Don't hit graph yet. Based on the way they presented the problem, can you tell anything about it by looking at it? Can you tell anything about the graph of it just by looking at the way it was given to you?
It's a -3 and +2.
Oh. Yep, you're right. Okay, let's fix that. I had it typed in wrong. I had my signs reversed. Sorry. That's correct now? No?
You had it. You had it right. Preston.
+3 and -2. What's your problem, Preston?
No, well, it can't hit the x-axis at -3.
Oh. Sorry. You're right. It will. It will hit the x-axis at -3 and +2 because those are factors of the, I'm sorry, those are zeros of the factors. And we can see the factored form because of the way it was presented. Is there anything else about it that you can tell just by looking at the form that they gave it to you? Do you think it will be fat or skinny compared to something else? Little skinny, why? Because of the, what up here? The 1/6. What about the x minus 2 squared? Doesn't that mean that the zeros of this function are -3 and 2 and 2? What about that? will bounce off at 2. That's another thing that we can tell. Just by looking at this without ever hitting graph, by the way it was presented, we can tell that this thing is this graph, whenever we get it, is going to cross at, what did you say, -3? Slam it right on through there. It's going to go right through one way or the other, either this way or this way. And at 2, right here, it's going to bounce. Tell you what else we can tell.
Starts low.
Starts low and ends high. Why do you think that? What's the degree of this polynomial?
3.
Why 3?
It's going to be x squared times x, which would be x cubed.
Perfect. Look, listen to what he's saying. If we were to FOIL this out, we would be multiplying this binomial times this one after we squared it. And so we would have an x term. The very first thing we would have is an x term times 2 x's here, x squared. We would have x cubed. Besides that, there's 1, 2, 3 factors. There's 3 factors. It's a cubed polynomial. Does that make sense to you? Not only that, it's a cubed polynomial with a positive leading coefficient. So it should start low and end high. You got to know this before next test, folks. Do you understand how we read that? Even though it doesn't start out x cubed, what we can determine it will be an x cubed function with a 1/6 on it. Odd degree, positive leading coefficient. It's going to hit the x-axis here. It's going to go slamming through this one, but bounce off of this one. It's going to start low and end high. So we've got a pretty good gist on what this thing's going to look like. Something like that, right? The one thing we don't know that we've never discussed so far yet is just how high this goes. We already know how low this one goes, but we don't know how high this goes. That's why we're graphing, so that we can get it, not just a gist of what's going to happen, but get it as perfect as possible hand-drawn. So I'm not certain this is going to be the case. I know this is the shape it's going to have based on what I read from the equation. But now I want to graph it to get that one high point. So I'm going to go zoom standard. So it's a 10 by 10 screen. How do I go about finding this so that I can plot it and get it accurate on my graph? Second, calc a maximum. We've done this before, folks. It's a maximum because it's a peak. Got to get to the left of that mountain. Hit enter for a left bound. Go climb over the top and come down the other side. That's a right bound. Don't guess. And it looks to me like it's at 1 1/3, -1 1/3, and up just a smidge more than 3. So here's my -1 1/3, and it's going to go up 1, 2, 3, and a little bit. That's hard to really graph, but it's going to be right there. So see, I haven't drawn it correctly. So I think I'm going to write, well, this one's okay over here. This one I'm not sure. I want to make it sure it's nice and smooth and doesn't come down this way and then jet off this way. It's going to peak out right there. So it's going to come down on this like this. And from there, it's going to come down towards this one and bounce off. If you would like, you can get one more point over here to make sure that your bend is heading in the right direction. I think I will. So I can use my trace key for that. I'm going to go trace. And I'm going to go over here to this other branch and go up a little ways and get one more point that I can shoot for. Like maybe about right there. That's 4 and almost 5. See what I'm saying? That's where I'm stopping. So here's my origin. 1, 2, 3, 4. A little teeny bit more than 4, not enough to show graphing. And almost 5. 1, 2, 3, 4, 5. Not quite, but almost there. And so you can see I didn't head that out in the right direction either. It's going to bounce off here, yes, but it's going to head up a lot sharper. Not sure about this one. Maybe we ought to do one of those. Make sure I'm going the right direction over there. Let's move the cursor until we're on our way down. Just use your trace. Go down a little ways and try and plot one more point so that you've got this last branch going down where it should do. That's -4 in a little bit, and it's -6 in a little bit. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6 and a little bit, about right here. So see, I missed that too. Would I mark that wrong on a test? You're darn right I would. Because you got your calculator to do the grunt work, you'd better be able to copy it well. So you're not only going to need to know the zeros, which we read from the graph, from the equation. You're also going to have to know where it peaks out and at about how sharply it takes off once it's done bending around. So you're going to need this one, There's the 2 zeros we got from reading it. We got this from the calculator maximum. We got this one by tracing. We got this one by tracing. You better put some points on there. I don't need a whole bunch, but it's got to peak out at the top where it belongs, and it's got to take off in the proper direction here on these. So you're going to need a couple. Think you guys can handle that? Can you do that? Okay. I'm going to expect really good graphs if you want full credit. So you may want to get some points to make sure that they're correct. All right. Let's look at example 3. Example 3 is very much like what we just did, but there's a lot more questions that you've got to answer. Notice that the very first part of the instructions for example 3 says graph the function. So we do that in exactly the same way we just did, but we have to answer a lot more questions. So go back to your y equals screen. Notice that the things we're graphing this time do not have factors, so we can't tell where the zeros are. They're just offered in standard form. So let's do the A part of example 3, and we're going to graph that thing in standard form, and we won't be able to tell the zeros till we get it done. X raised to the third minus 3x squared plus 6. One thing we can tell about this is that it will start low and end high, again, because it's odd degree with a positive leading coefficient. So that's what we expect when we graph it. Okay. We can also tell, now that it's been graphed, that it has only one real zero, and the other 2 are imaginary if we were going after them. Okay, that's what we can tell right there. But our objective here is to graph it and then answer a bunch of questions about the graph. So here we go. I'm going to find that first 0. I'm going to find this 0 first. I think it's at -1, so I'm just going to ask it what the value is at -1. Nope, it's not -1. So I'm going to calculate a value. No, a 0. Left, right. And it's at -1.2. So I'm going to have a 0 about right here. Okay. And I think I'll go down that branch while I'm already there a little ways, well, with a trace, and see if I can plot another point so I can shoot for the correct drop off. That's about -2 and -12. I don't want to count that far. That's about -1.5 and -4. Here's the origin, -1.5 and -4. 1, 2, 3, 4. This thing is dropping off in a big fat hurry. So I'm going to shoot for that point right there as soon as I'm ready to draw. I'm going to go find a maximum, calculate. I want this peak right here, so I climb around the top of the mountain. Don't guess. It's at 0. Do you recognize that this is read as 0? Because it's times 10 to the -6. Pretty small number. Pixel crisis. Do you see it? Watch for that E when you're reading things. That is at 0.6. Yeah? Y'all see it? You sure? That's 0. 0.6. Here's the origin. 1, 2, 3, 4, 5, 6. Got to come clear up to there. I'm going to go find this minimum so I can shoot for that. It doesn't come clear again, so I'm going to go calculate a minimum in that region. That's going to be stay to the left of it, go climb around the bottom of the ditch, come back the other side, don't guess. It's a 2, 2. 1, 2. Okay, it's going to bottom out there, and I want one more so that I can shoot that last leg off in the right direction. So I'm going to go trace. I'm going to go up a little ways till I find a point that I can plot. That's about 3 and almost 6. It looks like a series of points there, but we know how they can behave based on that, and so we start stringing them together. That would be a well-duplicated graph. Do y'all understand what I did? Why all the points on there? Okay. Now we've got a lot more questions to answer here. First one says, identify the x-intercepts and the points where the local maximums and local minimums occur and determine the intervals for which each function is increasing or decreasing. Wow, I wish I'd have kept track as I was going along. X-intercepts, that means zeros. This thing right here, do you remember it was about negative 1.2? 0? This is an x-intercept, and if you're going to put it right on your graph, you have to identify what you've got. That's an x-intercept. What else are we supposed to identify? Maxes and mins?
Yeah.
Okay. Well, this maximum, if you'll recall, was at 0.6. Put a max on that. This minimum was at 2.2. These other points were just to help put those legs in the right direction, so we don't have to put anything on those. They're not anything particular or important. So it says identify the x-intercepts. We did. The points where local maximums and minimums occur. We did. Now we have to determine the intervals for which each function is increasing or decreasing. Do you remember the definition of increasing and decreasing, or how to recognize it? Yes, always left to right. You must be moving to the right and asking yourself if you're going up or down as you do that. But you must always be moving to the right. And by the way, the intervals for increasing and decreasing are always x values for which this is happening. So I'm going to put it over here because I want to write it. It's a little cumbersome on there. You can write it on your graph if you want. But I'm going to say increasing, INC colon, and we need interval notation. That's the one with the parentheses and the brackets. Do you remember me telling you about those? No? Wonder if I did. Let me show you. Let me remind you. You tell me at any point, you go, oh yeah, I remember that. I just couldn't access my memory about it. If I tell you, for example, that x is less than 2, if those people can see that. If I tell you, if I give you this expression, x is less than 2, do you understand that it can be written this way? Negative infinity up to 2? Have you ever seen that before? No. Let me see how they want this expressed. Just a minute. They're going to tell us. Okay. They don't want interval notation yet. Never mind. I thought I had taught that to you, but that's a pre-calc notion, I guess. We're actually going to express this with inequalities. We're going to use less than, greater than signs. Okay. So, can you see that it is increasing? What's that? Can you see that this one right here, as we move to the right, is increasing until we get to x equals 0? And that this thing, you understand that this thing drops off forever. So if I was an x way out here, I'd have to go way down into the floor to even hit the graph. But if I was on the graph, I would be increasing until I got to 0. So it's increasing for all x's less than 0. Also increasing for x's greater than 2. Because look, once you get to 2, you start going up again. And you go up forever. So the only place where we're decreasing is in this little range right here, because that's the only place it's dropping down. So you say decreasing, and do you remember how you write between using inequalities? When the x values are between 0 and 2, it is decreasing. Does that make any sense? If x is more than 0 and at the same time less than 2, we are on a chunk of the graph that is decreasing. We good?
Yeah.
Okay, this is how you represent. You're going to have to use inequality symbol. This one, actually, to be true to the logic of the whole thing, this word should be or, not and. If x is less than 0, or if x is greater than 2, you'll be increasing. Yeah, you see that? Or makes better sense. If you are between 0 and 2 on the x-axis, you will be decreasing on this function. Very clear. Okay, we finally have everything done. We have the graph very, very well copied. We have located on the graph itself the points they ask us to, and we identified what they are. Then we have to look at the graph and find intervals for which it is going up and intervals for which it's coming down. X intervals. And you have to be able to write them properly with inequalities. Okay, let's try the B part. We'll go a little bit faster this time. We're going to answer the very same questions with the B part. As I graph it, knowing that I'm going to have to identify these points, as I graph them and find them and plot them, I'm going to write down those points so that I'm done when I'm done. You know, I've got them all done. I have to go back and say, what was that point again and what? We want to find maxes, mins, and zeros. So as we do it, we'll go that route. So here we go. B part, go back to your y equals, clear it out, type that in. Please don't just sit there. Do it with me. Start on a standard screen and see what happens. Okay, did that behave like you expected? Fourth degree polynomial, leading coefficient positive, starts high, ends high. But notice in the graph that we have, we can't see that minimum. But we anticipate, we understand that there will be a minimum down here, right? We just can't see it. We're going to have to find it. So I'm going to expand this to see just how far down it goes. I'm going to go to my window and I'll let my y minimum be negative 30 by 5s. See if I can see it. Still can't see it. Holy camole. Okay, we're getting closer though. Let's go to negative 50 by 5s. Oh, there we see it. Where is that thing? Well, let's look at the graph and see about where it is. If these are by 5s, this is 5, 10, 15, 20, 25, 30, 35, 40, between 40 and 50. No, I didn't count that quite right. But anyway, it's way the heck down there. You want to count that?
No.
Neither. So, by looking at this, before you start copying it, you may want to go to your graph, and the x-axis is okay, the way it's numbered, right? X is okay, but y's aren't. Then you want to put some things on here like 5. Maybe not the 10 because it gets your numbers too close together, especially the tiny graph paper I gave you. So if this is 10, then go to 15 here, so you're skipping every other one. 20, 25. So that I know how you're counting. That's good enough. That's enough. If you just do it either on the positive or the negative, I don't care. Give me 3 numbers so that I know how you're counting. And then remember to count that way when you go to graph it. So I'm going to take my trace key, first of all, and I'm going to go up this left branch a little ways. Get a point to plot. Oh my goodness, that's huge. Look at the y values. They're still gigantic. Well, now we're getting down there. So that's about negative 1 1/4 and a little more than 4. Here we go. Negative 1, a little bit, a little more than 4. 1, 2, 3, 4, a little bit. Okay, so this is my point that I'm going to shoot at to get that leg going the way it should. Head it off in the right direction. Now I'm going to go after this minimum right here. And by the way, you know what? I don't like, you can either turn this off or we can get some more y's up here so that this isn't interfering with the writing. I'm going to go for the more y's. So I'm going to go back to my window. I'm going to let my y max go up to 25. Maybe that's not even enough. We'll see. Okay, I'm able to see quite a bit there. I'm going to go after this minimum. So we go calc, minimum. And that's at about negative 1/2 and down 6.5. So there's a minimum. Oh, counting by 5s. Let's try that again. Here's the origin. We're going to go back 1/2 and down about 6. That's about right there. Sorry. I know this is boring, you guys. Stay with me. I'm going to calculate that next one, which is a maximum. Oh, by the way, I should have done that. Hang on just a minute. I got to go back. Calculate a minimum. It's going right to it. I got to put that in here. It's negatives. Wait a minute. Was it a minimum?
Yeah.
It was a minimum, but I'm wondering if I calculated it. Because I thought it was negative 0.5 something. Yeah. Negative 0.57 and negative 6.5. I'll find where that is because I'm going to run right into it. Okay. And Now let's go find the maximum. I know this is boring. Stay with me, please, because you're going to have to do it. Copy this very carefully. It doesn't hurt to practice. 1.1 and 5.1. Remember how we're counting. This is 1.1, 5.1 is just right there in that little corner right there. Okay, let's go after the other minimum. This is the deep one. Holy moly. Almost 4. I'm going to say 3.96 and negative 43. 1, 2, 3, 4, 5, 10, 15, 20, 25, 30, 35, 40. 45 would be right there. 43 is about right there. That's the other minimum. And according to this, it is located at 3 point. And negative 43. That's good enough on the second one. This is a min. We need one more to get that leg to shoot off, right? Maybe we could do this one right here. So 1, 2, 3, 4, 5. It's about 0.5. Hey, here we go. Wanting to shoot for. Where'd my point go? Did I erase it when I erased that stuff? There's a max. No, that's not a max. That's going up that way, right?
Yep.
Okay, it's going to turn right here, and turn right here, and turn right here, and then head up like that. There we go. It's 5.1. Fix that. Where is it increasing?
It's increasing from like.
If you have those points on there, you can tell and use those points that you already have written on the graph. It's increasing.
It's like from point negative 0.57. X.
1.1.
Good. Do y'all understand that? That little jog of increase right there? Where else is it increasing?
From 3.96.
Where? How big? So X is more than
Yeah.
3.96? Is it increasing anywhere else?
No.
Okay. Or is it decreasing?
From 1.1 to 3.
This is how you write it.
3.96.
Huh?
3.96.
Where else?
Is it X? Is
Less than.
less than or greater than
No,
negative,
less than, just less than.
negative 0.57.
Crazy, huh? Can you do it? If you get the points written on there as you graph it, then you can do this stuff and you'll have the points sitting right there for you. They are X values that you're talking about. Crazy, huh? There you go. And if your Y values drop too far, you're going to have to renumber your axes. Make sure you do that. All right. Last thing I want to show you. And this you have never seen before. And it's going to take some effort on your part. So while that last part was really boring, you guys are all sitting there on your hands like this, it's okay. I'm using you as an example. Like that. Or like Alexis, he's all crashed back like this. And some of you are in there. I got another hand on the face. And a lot of you are doing something else, like on your phones or something. She's always paying attention. Anyway, I need your attention now. Gears are going to shift. And you got to shift with me. You got to go to a new place with me. This is an extremely important concept that you will see and have it revisited over and over and over again for as long as you're taking math. Wherever you're going, whatever you're going to study and you're taking math, this will show up. It's an interesting little concept. It's called even and odd functions. Now you might think that an even function is always one that has an even degree, or an odd function is always one that has an odd degree. That is not what's going on here. It has to do with symmetry. There are two kinds of symmetry that we will discuss. I think I'll leave that up here and draw my symmetry stuff over on that board. Hopefully everyone will be able to see. Okay, here's the deal. If a function is even, then graphically, and most of the time you can tell graphically, sometimes you can't tell, and you're gonna have to do the algebra on it, so you're gonna have to learn both. Even functions have line symmetry, and the only line we will consider is the y-axis. If it has y-axis symmetry, it's even. So here's an example of an even. This is the most classic even function there is. You know this one. Well, that's really crappy, but pretend it was drawn properly. There's your parabola. Your parent function parabola. Do you understand that this is x squared, by the way. Do you understand that if I were to move that up and down like x squared minus 4, that would also have x or y-axis symmetry? Because it would just move it down to here and go up. And it would be, this line would split it right down the middle like a mirror. Do you understand what I mean by line symmetry?
Yes.
Y-axis symmetry only. If instead you transform this parent function this way, if you do it y equals x minus 3 squared this way, you know that one's going to move it to the right 3. And while it is still a parabola, with this line symmetry is not an even function because it's not the y-axis that splits it. So this one is an even function. This one is not. This one's your classic one. If you have a 4th degree polynomial that behaves this way, I'll show you. By the way, this one that we were looking at that was on the calculator that we graphed right here, this is not even. This doesn't reflect over here. But it's quite possible for 4th degree polynomials to do that. They go like this. They might come down like, come down here, up to here, back down, up like that. Can you see that that has y-axis symmetry?
So it splits it in half, basically.
If this serves as a mirror, so that this, when you flop it over the y-axis, lands right on top of that, then it has y-axis symmetry and is considered an even function. You see this one is not even though it's a 4th degree? It's not even. Okay? So do you think you've got a feel for at least looking at and seeing what an even function is? Yeah. Okay. Odd functions, that's what we did a little bit with yesterday. Odd functions have not line symmetry. They have what we call origin symmetry, or in a general way, point symmetry. But the only point we will consider is the origin. So the classic one for this is x cubed. We saw that yesterday. It comes down kind of like this. Like pretty crummy, but pretend it's nice and even. It might be a little better. But this is x cubed, and we say that this one has origin or point symmetry. The particular point, the only one we will consider is the origin, 0, 0. It has to go through that point. And what it does in the first quadrant is it's kind of like a double reflection. Imagine this. This might be a little hard for some of you to handle this, but I think you get it. If I took just this branch right here, just this one, and I reflected it over the x, it would look like this. And then if I took that and reflected it over the y, it would look like that.
Yeah.
So it's like a double line symmetry. That's not what we're going to call it. It's point symmetry. It does the same thing in the first quadrant as it does in the third. Y'all remember your quadrants, right? 1, 2, 3, 4. It could also do something in the second quadrant as long as it does the same sort of thing in the 4th quadrant, but it must pass through the origin. Okay. That's not entirely true. I lied. It has origin symmetry. This particular one right here also has origin symmetry. People up there can still see that. Close. Okay. I lied about it going through the origin. Let me show you one, and then you see if you understand that it still has origin symmetry. This is the graph of the function 1 over x. It's asymptotic, they call it. Can you see that that has origin symmetry? Yeah. Reflect across the origin, you get the same thing, even though it doesn't pass through the origin.
Yeah.
You see what I'm saying? So it doesn't have to pass through the origin. It just has to do the same thing in kitty corner quadrants. You think you can recognize it when you see it? Okay. So that's the graphical way of recognizing them, and you can always graph your functions and see, and most of the time you'll be able to tell, but sometimes you can't because it's so big and so slightly off that you can't tell just by looking. And so in those cases, you're going to need to know the algebraic definitions of these. So now we're going to look at the algebra of this. We're also going to refer to the graph once in a while too. But an even function has this property. If f of x is exactly the same as f of negative x. If this function, when you plug x in, just a regular old function, whatever it is, gives you the exact same thing if you have if you plug negative x in and do the math on it and get exactly the same thing that you had before, then it's even. And here's why. I'm going to draw the graph on here. I'm going to erase it and then show you an example. But here's why. Think about this with me for just a minute. On the standard parabola that we had, and it will work for any even function. I think you'll be able to tell in just a minute. If I, for example, were to look at 2, and I went up to the graph, plot a point, this would have to be 4 if this was x squared, right? If I let x be 2, then y's got to be 4. So this is a point on the graph. But look what happens when I change the sign on the x plug-in to -2. What do you get? The same thing. So f of 2 is exactly the same thing as f of -2. They're both 4. That's a property of even functions. If you go out the same distance to the right as you do to the left, you will have to go up just as high to hit the graph if it has y-axis symmetry. Does that make sense to you? Now here's how you prove something's even algebraically. This property has to hold. So this is how you would do the algebra on it if you were trying to show it. Let me grab one here that's going to work. Let's consider the B part of example 4. G of x, they're calling it G instead of f, it doesn't matter. It means G of x equals G of negative x, x to the 4th plus x squared minus 1. I'll go ahead and call it that. X to the 4th plus x squared minus 1. That's what I'm looking at here. That's the function I want to have, and I want to know if it's even. I'm testing to see if it's even. So what I want to know is, what is f of negative x? So I'm doing this side. I got this side over here. This is it. I want to do this, which means to plug in negative x for all the x's. That's negative x to the 4th plus negative x to the 3rd squared minus 1. You see the plug-in? Now, when you 4th power negative x, it's negative x times negative x times negative x times negative x, which is positive or negative? Positive. This is negative x times negative x, which is what? Did we get exactly the same thing back? We sure did. That's evidence that it's even. Because when you plug in negative x, you get exactly the same function that we started with, which is f of x. Following that? When they are odd, it's slightly different. The odd property, this is the even property that has to happen. This is how you test it. The odd functions have this property. F of negative x is equal to negative f of positive x. So not only do the x's switch signs, but so do the f's, if you will. Consider our classic odd function, which is x cubed. Think about this with me for a minute. This thing goes up like this, and it may not be well numbered. Just go with me on it. If I go for a 2 out here, what's going to be, what y value am I going to hit when I go up to here? No, 8. We're cubing it. Right? If I go to the opposite of this, which is -2, bad graph. It's not going to show up right. It's not going to work out very well. I'll go a little bit farther up. If I go to -2 here, and I go to head towards the graph, where am I going to land? At -8. So take a look at this. If I go to -2, the value is -8, yeah? If I go to +2, the value is the opposite of -8. We'll try that again. Let's try going this direction with it, see if it makes any better sense to you. If I plug in a +2, then the y value that goes with it is what? This thing right here is what? 8. Slap a negative on it, this value is -8, right? What is f of -2? -8, which is what we had over here. So that's true of all odd functions. If you go out and up, you do the very same thing if you go left and down. It also works if you go this way, because if you go out right and down, then on this one you go out left and up. The same amount. You see what I'm saying?
Oh, that's really cool.
That's evidence, algebraic evidence that it's odd. So this is how we test that. It's kind of rough, so hang in there. Can be negatives. So let's consider x to the 3rd minus 7x. If f of x is equal to x to the 3rd minus 7x, then what is f of negative x? This is f of x. I got to build this side. So that would be negative x to the third minus 7 times negative x. Are you with me so far? On this side, I take whatever f was and I distribute a negative, which is negative x to the third plus 7x. So this is negative f of x by distributing a negative because it was on the outside. This replaced all the x's here with a negative, so this is f of negative x. Are you with me? Now we got to clean them up and see if they're the same. If I cube this, I will have 3 negatives giving me what? Negative x cubed. When I simplify that, because I got 3 negatives and an x cubed. Okay? And here I have negative 7 times negative x, which is positive 7x. Oh, look at that. This is an odd function. This, which was what we were testing, this is an odd function. Okay? They're not all like this. I mean, there's a lot of odd functions that are trigonometry and logarithms and things like that that end up having different aspects of things. But this is polynomial that's odd. This is an example of that. Now let me show you what happens if it's neither. X cubed plus 2. That's f of x. I'll tell you a little secret here. When you're testing these things, you do not ever have to test this one for evenness. It will never be even if its degree is odd. It may also not be odd. But you don't have to check for evenness here, and you do not have to check for oddness here. So in other words, you don't have to run both tests on everything you run into. This one I'm only going to check for oddness. That's the only shot it's got to be in either one. You understand? Okay, so what I'm going to do is I'm going to find f of negative x, which would be this. Oops, yeah, x cubed plus 2. This is f of negative x that I'm looking at there. And I want to know, that's the question mark, is it equal to negative f of x, which means distribute a negative. That would be negative x cubed minus 2. Did y'all see what I did? Or not?
Yeah.
You're not following? Okay, I need to check out this aspect right here. So what I did is I took f, which was this one, and I found what f of negative x would be right here. That means replace all the x's with negatives. And then I also, on the other side, put negative f of x, and that negative out here means to distribute a negative through f. That's negative x cubed minus 2. You see it? I want to know if those are the same. So I cleaned this up over here. I got an odd number of negatives, so that's x cubed, negative x cubed plus 2. And over here I have negative x cubed minus 2. They are not equal, so this is neither odd or even. Not every function is odd or even. A lot of them are neither one. And think about that for just a minute. This is x cubed moved up 2. And what that does is goes up here before it, because it's like that. And that does not have origin symmetry. You get told that it was not by the graph, if you graphed it. This is the algebraic explanation. Okay? Just to verify graphically on these, we've come up with an even and an odd and an either. I want to show you these just real quick so you can recognize them graphically as well. It's the same ones I graphed on the other page over there, folks. So here we go. I graphed that first one. It was x squared plus x to the fourth plus x squared minus 1. X to the fourth plus x squared minus 1 graph. Oops. Let's go to standard screen. That's pretty obviously y-axis symmetry, right? Okay. Next one is x cubed minus 7x. X cubed minus 7x. That has pieces of it in all 4 quadrants, but do you recognize it as having origin symmetry? This little lump right here reflects over here in the 4th quadrant. This branch going up here reflects over here across the origin. So this has origin symmetry. Besides that, we showed it was odd. So if you're looking at that going, I can't remember it, you can always go this route and see if it's true. And the other one is x cubed plus 2, which I already showed you, but I'll show you anyway. Plus 2, delete. See, it moves it up 2, so it doesn't have origin symmetry. Lost it. Everybody okay?
Wait, so what is that negative 2 on the Well, if this was a positive 2, would it be an R function?
No, these are all functions.
Or, yeah.
But no, it wouldn't be odd. If we did x cubed minus 2, all it's going to do is move this one down 2, and it still doesn't have origin symmetry. You'll end up with a different sign for 2 on either side, either way. Okay? So that's the algebra way to do evens and odds. These things right here in the box, they are the properties that you have to establish algebraically if you're asked to prove it, that they're either odd or even. Those are the properties it's got to have. The ones in the box. Those are the properties of even and odd, if you can see that, if you're watching. Okay, that didn't show up. And remember this too. If it's a polynomial, you only need to check for oddness or evenness based on its degree. You don't need to do a test, both of them. All right. That's it. You're going to be doing a lot of tedious graphing today. I hate to tell you, but you got to get good at copying. Finding different aspects. Okay, so those of you doing it on paper, here's the assignment. And if you need some graph paper, make sure you grab it before you leave. The assignment is 3 through 7. 9 to 21, odd. 25 to 45, odd. And 52. I want you to look with me for just a minute before you start out. I want you to look at number 17, 19, and 21. Look at what the instructions say. Find all the real zeros of the function. How are you going to tackle that? I didn't show you how to do that. Graph it and find them, or polyroot find it, but don't write down the imaginary ones. That's all. Okay? All right. There you go. All done. See you later.